Welcome to lecture 13. Let us start looking at properties of group. Point groups a little in more details. So let us start with summary of group definition. So we said when symmetry elements are group elements, which is symmetry operations, which are related by four properties, then these are defined as point groups, right? So the first property in that is closure property, which defines that if G is a group consists of various elements, then AB equals X, any group element, such that X must belong to G. Similarly, if A square is equal to Y, such that Y should also belong to G, right? So that is a closure property. Next property is identity element. So group must have an element E which must commute with all other elements and leave them unchanged upon combination. Okay, so I'm just briefing you those properties again. Closure, identity. Third is group elements must follow associative law. Associative law of combination, which is A, B, C is equal to A, B, C, right? So this is self-explanatory. We'll look at certain examples to explain all of this again. Then fourth is inverse. That is, every element must have an inverse which must belong to group, right? So these are the four properties which group elements must follow so that they can be called as a point group, right? So let us take a few examples. Let's start our examples from simple mathematics that we know already, and then we will go to symmetry operations. So let's see. This will help us understand this group properties much more. So consider a set. So let's say call it example 1. Consider a set of integers including 0. So that means I is a set such that you have dash 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 -3, -2, -1, 0, 1, 2, 3. So this is a complete set. Now let's see if all the members of this group follow the four properties or not. Okay, so the closure property, and in this case for closure property we will say that combination is equal to addition. Okay, so we'll not be considering product as a combination, we'll consider addition as a combination. So closure property, so sum of which tells you that sum of any two integers is an integer, and this will belong to group I, right? So you can take any integer from this, and if you take a sum or combination, the result will belong to I. So the first property is valid. Second property is identity. So does it have an element which combines with other elements to leave them unchanged and is also commutes with those? So that element is 0. So for example, 0 plus 1 is equal to 1 plus 0 is equal to 1. So it leaves them unchanged, and then it's also commuting with all those elements, right? So identity also applies. Now next try associativity. So again, this is all in when combination is equal to addition. Okay. So for associativity, if we say that minus 3 plus minus 2 minus 1, this must be equal to minus 3 minus 2 plus minus 1, right? So this holds. We all know that it will hold. So associativity also applies. And inverse. So inverse is every integer has an inverse. So for example, 2 is inverse of minus 2. Remember, it's a addition as a combination. So 2 will be inverse of minus 2. 3 is inverse of minus 3, right? So they are all part of group. So inverse also applies. So that means I forms a mathematical group under addition. Okay. Now let's say example 2. Let's say if we consider the same group, but now we say that the combination is product or multiplication. Okay. So in this case, let's see the closure property. Does it hold true? So minus 2 into minus 3 is equal to 6. So product of any two integers is a third integer. So closure property does hold true. Then identity. So 1 is an element which leaves any other element unchanged and also commutes with them, right? So identity also holds. Now associativity. Does it hold? Let's see. So associativity means 2 into 3 into 4 like this is equal to 2 into 3 into 4. So that should also work. Associativity holds. Now let us look at inverse. So inverse of 2 is 1 by 2. Okay. In the previous case it was minus 2. In this case it is 1 by 2 because we have changed the definition of combination, right? So inverse of 2 is 1 by 2, which is not part of I, right? So inverse does not hold. So that means I does not form a mathematical group under combination. So that's example 2. Okay, let's look at more examples. Let's say we all know cube roots of unity. That is, if you take cube root of 1, we get 3 solutions, right? 1 omega omega square. How do we get this? Let's say if z cube is equal to 1, this is just a refresher, and to solve for z, you can factorize it as z minus 1 into z square plus z plus 1 equal to 0, right? So you can do this factorization, and this gives you first root as z equal to 1, which is an obvious answer, and the other two roots are, we can say z1, z2 will be equal to minus half. This is the quadratic equation, so you can solve it, plus I root 3 by 2, and this is imaginary, so z3 is minus half minus I root 3 by 2. Okay, so now it also, so you can call this as 1 and this as omega and this as omega square. Okay, so that's why I write 1 omega omega square. So as it turns out, if you look at this, if you square this and expand this, you will get, if you square z2, you will get z3, or if you square z3, you will get z2. So if you call one of them as omega, the other one becomes omega square. It doesn't matter which one you call omega, which one you call omega square. Both are related by square relation. You can test it yourselves. So this is the 10th class mathematics, which I'm not going to discuss. So let's go further. So now let's say that this particular group, which is defined as cube root of unity, does it follow the four properties? So let's test the closure property, and in this case the combination, in the closure definition, we will consider as product. Okay, so now let's see, for closure, product of every element must be an element from the group, right? So 1 into omega is equal to omega, omega into omega square is equal to omega cube, which is equal to 1. So this is part of group, this is part of group, and the third product is 1 into omega square, which is omega square. This is also part of group, so closure property holds, right? Then the second property is identity. So for identity, we know that 1 is an element which, when multiplies with omega, leaves omega unchanged and also commutes with omega, right? So identity also holds. Similarly, you can show associativity will hold, right? That is not to be shown now, you can show it, and also inverse. Okay, so we can say that omega into omega square is equal to 1. So that means omega is equal to 1 by omega square. So this implies that omega inverse is equal to omega square, right? So omega square, omega inverse is omega square, and omega square belongs to group G. Similarly, we can show for rest of the members. So if you take 1 into omega square, again you will see this will hold. So inverse also holds. So that means the cube root of unity form a set which forms a mathematical group. Okay, so you can take some home assignments here. So one is set of real numbers under multiplication. Okay, then you can also look at cube roots of -1. Okay, so we have done it for +1, you can do it for -1. Okay, and I think these two examples will be sufficient for you to understand that how the four properties are used to define a particular set, whether that particular set will be called as a group or not. Okay, so now let's also look at certain properties, recall some other properties. So we have also discussed product of symmetry operations. Remember that we have done if we say x into y equals to z, we say that this operation is applied first and this operation is applied second, and this is the resultant. We had seen that before, right? So, or in other ways, if I say that if I start from a molecule I and I apply Y, I get, let's say, E1, then I apply X, I get E2, which are equivalent configurations, and this can be achieved by Z, right? This is what it means by product of symmetry operations. So that should also be very clear. Now let us look at an important property of product. So as it turns out, reciprocal of product of two or more elements is equal to product of reciprocals in reverse order. So what do I mean by that? So mathematically you can write it as A, B, C, D, E, and so on, reciprocal of. So reciprocal of product of two or more elements, which is written over here, is equal to product of reciprocal in reverse order. That means E inverse, D inverse, C inverse, B inverse, A inverse, right? So if I say this, so product of reciprocals in reverse order will be equal to this, right? Now how do I prove this? So let's try to prove this. So if we say, let's consider three elements for now. If A, B, C are three elements of group G, then we can write A, B, C is equal to D, right? So now multiplying by C inverse, B inverse, A inverse on both sides, what do we get? Let's see. A, B, C, C inverse, B inverse, A inverse gives you D, C inverse, B inverse, A inverse, right? Now this CC inverse will become E, right? So I can take this out because E commutes with everything. So I can write it as A, B, B inverse, A inverse, and E I don't need to write. This is equal to D, C inverse, B inverse, A inverse. Similarly, I can write this as E. Again, I can write A inverse as E. So this is nothing but E is equal to D, C inverse, B inverse, A inverse, right? Now I can take D that side, or what I can do is multiply with D inverse on both sides. So what do I get? D inverse E is equal to D inverse D, C inverse B inverse A inverse. Now I can skip this thing E, so I can just write D inverse. D inverse D will also be equal to E, so that also is not to be written. C inverse, B inverse, A inverse. So E is like mathematical 1, so which is not required if you are writing it in multiplication, right? So, and we started with assumption that A, B, C is equal to D. Product of these three elements is equal to D. So we can now replace this as A, B, C inverse equals to C inverse, B inverse, A inverse, right? So that's very easy to see. So this is one important property that we'll be using every now and then in various things. So that's why I thought it is better to show it. So now let us go to something called as group multiplication table. So why do we need to look at a group multiplication table? So basically what it means is it's also short formed as abbreviated as GMT. So basically it consists of product of all possible symmetry operations in a given molecule. So how do you write it? For example, let's say if you have a G4, so G4 means that a group of order 4, which is consisting of E, A, B, C. Okay, so let's also define order at this point. Order of the group is denoted by small letter h is equal to number of non-redundant symmetry operations, okay, in a particular group. That will be called as order of the group. So now let's see what is a group multiplication table for G4. So when I say group multiplication table, I draw it as a table. I write G4 here, and then I write E, A, B, C, and then in column also I write E, A, B, C. Okay, now E into E will be equal to E. Now in this case I multiply this as, I write this as first, or this one will be operated first and this one will be operated second. Okay, so then that means it will be written as AE, because this is my first operand and this is my second operator. Okay, similarly here it will be written as BE, CE, and here it will be written as EA, EB, and EC. Now let's also write down, this will be AA, this will be BA, CA. We will see how to solve this. Then this will be AB and AC. This will be BB, BC, CB, and CC. So also one important thing, since no two group elements are same, no two products are same. And products must belong to group, that we know from closure property, right? So all these products must belong to either of this EABC, but none of this product should be repeated. So for example, in any particular row or any particular column, all the products should be unique, right? Because all the group elements are different, so their products should also be different. So their product should also be unique. So this leads to something called as rearrangement theorem. So what is rearrangement theorem? It says in a group multiplication table, each row and column lists each element in the group once and only once. This means it follows that no two rows or columns are same. Okay, so both these rows and columns, all these rows and columns must be different. So let's now try to see how to populate these group multiplication tables. So let's start with the simple case of G2. So G2 will be order 2. That means only two elements. One has to be identity and second can be any element. So EA. Now if I multiply E to E, it will always be E. If I multiply E to A, it will be again A, right? Similarly, A to E will be A to A will be, now it has to be E, right? Because it cannot go out of these two elements. The product has to be closed product, or it has to follow the closure property, and it also complies with rearrangement theorem. So because this row reads as, this column reads as EA, whereas this column reads as AE, right? So this is not same as this, and similarly this row is not same as this row. Okay, so now let's also try G3. So E A B, E A B. Now first row will be, because it is multiplied by E, so it will be same as EAB, and similarly this column will be EAB. Now we have to write here what is the product of AA, and this will be BA, this will be AB, and this will be BB. Okay, so now let's see if, let us suppose if AA is equal to E. So if we replace this as E, then BA, this product has to be, the only option is that if AA becomes E, then A is already taken, E is here, then the only option that can come here is B, right? But now B cannot come here because B is already present in this column, right? So two columns cannot have same elements, or two rows cannot have same elements at the same column place, right? So if I put this as E, this has to be B, and you cannot have two B's in the same. It's like a Sudoku puzzle, right? Where you cannot repeat any digit when you're playing Sudoku. So very similar to that. Okay, so that means this condition is not valid. So this leaves us as, you have to keep AA as B, because AA now cannot be A because we already have A here. So AA has to be B. So if AA is B, this implies that BA has to be E, right? So then you can replace, you can write here B, A is equal to B, BA is equal to E, and that leaves A, B. This becomes your E, and this becomes your A, right? So now you notice very interesting thing over here, that AA is equal to B and BA is equal to E, and BA is nothing but AA. So this becomes triple A is equal to E. So if you see that A is equal to A, so now if you correlate A to the power 1 is equal to A to the power 2 is equal to B, A to the power cube is equal to E, right? So this type of group where every element can be obtained by a single element and its powers is called a cyclic group. Okay. Also, it is important to see, you can verify this yourself, groups of prime orders where H is equal to 2, 3, 5 and so on are cyclic and abelian. Abelian we have learned earlier, cyclic we have learned today. So groups of prime orders are cyclic and abelian for all such groups. Okay. So now let us, I think it's time to wrap up this part, group multiplication table. But before going, let us take some home assignment. Populate GMT of G4, G5 and G6 and see, for example, in case of G3 we have seen, or G2 we have seen, that there is only one way of filling this group multiplication table. Let's see, also find out how many possible ways are there to populate above GMTs. Okay, that's first, and also do write GMT of NH3. Okay, let's, you try to find out what is the point group, what are the symmetry operations. So what you have to do is list down all the symmetry operations here, list down all the symmetry operations here, and then find out all the products of these symmetry operations to populate the GMT. So this will be, so I'm not going to tell you what is the order, what are the symmetry operations, so you try to exercise it. The certain products will be easier to fill, while certain products you will have to actually carry out all the operations and do it. So this will be easier once you have the GMT of NH3 ready with you. This will be easier to further go look at the properties of subgroups and classes, and also when we take NH3 example will be easier. So try to do it yourself. If you have any difficulty, we can always discuss in the interaction class. Okay, I think that's all for today. Thank you.